Well, thank you very much for having me. And I want to describe an idea which, well, it isn't all that new because it's about 15 years old, but I suppose that counts as new. I want to talk about something which I claim happened before the Big Bang. Now, you see, this represents a change of mind on my part, which used to think, like Stephen Hawking and many people, that the Big Bang didn't have any before, because the notion of before and after didn't mean anything when there wasn't a universe around, and so you couldn't even talk about before. Well, I'm going back on that, and I claim that there is something before. But before getting to that, let me describe the universe. This is a picture which more or less describes the history of the universe as we understand it. I need to explain a couple of things about this picture. Well, first of all, time is going up, and the Big Bang's down there, and it expands out, slows down a bit, and then it starting to do this what they call the accelerated expansion that seems to be taking place, although there was some dispute about that in the early discussions I was involved in. But I'm taking the view that it is doing this accelerated expansion. Now, a couple of things about this picture. I just want to show you that you could take sections that represent one moment in time, if you like. That you imagine that blue plane sliding up, and the universe at any one moment is considered to be that intersection. Notice it looks like a line rather than a three-dimensional space. You've got to make allowances, add a couple of dimensions to get the picture right. So this is really 3 dimensions and 1 of time. So that's the first thing I wanted to explain about the picture. The second thing is, what's all this frilly stuff at the back doing? Well, that's in there because I don't want to prejudice the issue as to whether the universe is spatially open or closed. These are nice pictures of, well, due to M.C. Escher, the Dutch artist. And here we have the closed one. You see, you imagine space as being the surface of that. Again, you've now got to throw away 1 dimension, because it's really a 3-dimensional version of that. That's the closed case, where the curvature is positive. This is the flat case, where it's Euclidean, and this is the case which is called negative curvature. I want to come back to this picture later on, because it's a particular representation of this geometry, which is called hyperbolic geometry, where these angels and devils. I mean, Escher has very cleverly used the same creatures to illustrate these 3 completely different geometries. Now, the current view is that it's more or less flat, but of course that means we don't really know, because we haven't seen the whole thing. It might curl around, or it might do this. I'm not going to worry about that. The frilly stuff at the back is just to say I'm not caring which it is, and I don't care what happens at the back, at least for this discussion. I do care to a certain degree, but that's not the point. Now, the next question is, what's all this at the beginning? There's the thing called inflation. Now, if you look at any modern cosmology book, whether it's popular or whether it's technical, they talk about within the first 10 to the minus 32 seconds, that means 1 over the fraction of a second, that is, which is something 32 digits long. Ridiculously tiny fraction of a second. The universe was supposed to have inflated. Now, to get you some picture of what inflation looks like, I'm putting a powerful magnifying glass here to have a good look. And what do we see? I should point out that we don't see that. That's the handle of the magnifying glass. But what you see is something very similar. Let's back up to what you see in the remote future. So it's sort of a model of what's happening there, but tucked in at the beginning. Now, you see, the reason I was not keen on mentioning it here, there's 2 reasons. One is, of course, it might be there, tucked in, and that's why we need the magnifying glass. The other reason is I don't really believe it. So this is putting me in a bad minority, but I'm already in a minority, so that doesn't matter too much. So I'm trying to say I don't believe in this. But there are good reasons to believe in it. Let me say what a bad reason is first. One of the reasons people put forward is that you want to explain the curious fact that the universe is really very, very uniform. And this was one of the explanations, that somehow, if it was very irregular, then this inflationary phase will stretch it all out flat. Now, I never believed that argument, and the sort of reason is the following. Imagine that the universe was collapsing, so time is now still going up, but then there will all be sorts of wrinkles, there will be black holes, And this picture now is not, I wanted to use another picture, but I couldn't find it, so you have to imagine it. A very, very complicated thing up there, which doesn't look like that nice clean little point, but a great mess up there. That's the sort of thing you get when black holes, you see this before black holes will form, and they'll congeal and make a huge mess, and it would look horrible, not like that nice point. So why wasn't it like that the other way around? You see, the equations of Einstein work just as well in time one way or as the other way. So why was it not that huge mess at the beginning? And inflation doesn't solve that equation. That doesn't solve that problem. But I want to talk about that because this is a key point of the argument. And for the moment, I'm not going to say why. I'm just going to say what, in a certain sense. And to do that, it's useful to go back to the Escher picture, which I just showed you. And now this is a spatial picture, not time in it, so it's just space. But these angels and devils inhabit this infinite universe. So although it looks to us as they're getting smaller and smaller to the edge, you have to imagine, well, you can choose the angel or the devil, whichever you prefer, that you are the same size, no matter how close to the edge you are. So these fellows, or fellowesses, no matter where you are, you will see it looks just like the beginning. And the transformation involved here is what's called conformal. That is, you squash down in all directions by the same amount. So you're not just squashing this way, but you're squashing that by the same amount. And it's a very nice kind of geometry. Angles, like the angle on the wing of this devil, will be the same no matter how close to the edge you are. The eyes will be the same shape, no how close to the edge they are. They're just a different size. So it's a kind of geometry, a very beautiful kind of geometry, where you're not interested in distances, but you're interested in shapes, small shapes, or if you like, angles. And this is a very crucial part to the argument that I want to give here. So these angels and devils, from their point of view, the universe is completely infinite. We look at it from a different perspective. We allow ourselves to squash the infinity down in this conformal way. And you could imagine stepping from here out to there. They can't do it, but you could sort of imagine something might do that. So let's come to that. Okay, now I've now applied this to the universe. This was the picture, drawn smaller now, of the history of the universe. Keeps on going out to infinity, but that infinity, like in the angels and devils picture, is squashed down to this boundary here. So that represents the infinity of this universe. And that's quite accepted thing you can do. The universe, as far as we understand it, in the very remote future will smooth itself out in a way which allows us to... They're very general theorems. There's a theorem due to a German, Helmut Friedrich, who established under very general circumstances this conformal squashing down can be done. So there's no argument there. What I'm doing here on the beginning is the opposite thing. I'm stretching out the Big Bang to make it look like a nice smooth surface. Now that is not something which generally happens. It only happens when the universe starts out very, very regular and smooth in the way we seem to see it. And there's a thing I used to call the Weyl curvature hypothesis. Not even bother to explain what that means because it's a bit technical. And my former student and colleague, Paul Todd, who had another way of saying it. What is it? It says that the beginning of the universe is conformally nice and smooth, so you can do this. That's a hypothesis. If you adopt that hypothesis, then you do get this universe which is sort of smooth in the way we see. And it's very important for this thing called the second law of thermodynamics. The second law of thermodynamics says that this thing called entropy, which increases as you go, as time increases. And the thing is that we see in the universe observationally that it looks as though the entropy is very, very high at the beginning, when it should be very low because it has to start low. How is it low? It's low in gravity, which means that the universe was made. I don't really want to go into that argument. I shouldn't even started it because it's key to the description, but it'll distract me too much for what I want to say. I just say there's good reason for saying that this can be stretched out. It's very nice. It solves a lot of problems if that is the way the universe, for some reason, stretched out like that. What's the reason? Well, here's what I'm saying the reason is because this, our universe, as we think of it, starting from the Big Bang, ending up with this eternal exponential expansion going on and on and on, getting you more and more boring as as time goes on. And the argument is that our universe, as we thought, is not the whole story. That this future, remember the Escher picture, can be squashed down, and now it becomes the Big Bang of the next eon. And so this is what I call conformal cyclic cosmology, that we are here. There was one of these eons, I'm calling them an eon. I looked up in the dictionary to make sure an eon, A-E-O-N, was not an actual length of time. It seems to be it's a long time, but not a definite length of time, which is fine by me. So I've used that term here. A cosmic eon is that. But I'm claiming there was a cosmic eon preceding us, one later than us, one preceding before, and so on, and they just continue indefinitely. Now you see, you might say, well, it's a bit hard to swallow, and that's what lots of people say. It's hard to swallow because isn't the remote future very, very different from a Big Bang? Well, first of all, it's very, very rarefied. It gets the density goes down and down and down and down. It's extremely cold. The temperature goes down and down and down. What's the Big Bang like? Density is huge. The temperature is enormous. But you see, when you do this transformation, I did with the angels and devils, the conformal squashing or stretching, it makes when you stretch it, then big temperatures go down and the densities go down. When you squash it, the temperatures go up and the densities go up, and they match. So they physically match as well as geometrically matching. Now there's one little catch to all this to do with, well, I'll come to that in a minute. Before coming to that, let me talk about black holes. I did mention them before. Now, this is a picture of a black hole. It's not the normal thing where you see a black splodge in the middle of something. This is a space-time picture. So we have time going up there, and this is matter collapsing down, and this thing here is the horizon. So I have time in one dimension, and I managed to get sort of 2 dimensions of space in. Good, there's another one, but at least I've got 2 in, imagining it going round and round like that. And that is the picture of a black hole. It's a pretty good picture, really. Now, the point about the picture are these cones. Now, what are those cones doing? I have to talk about the cones. They're really important. Now, here is what's called a light cone or a null cone. You have to imagine in the space-time, 4-dimensional thing, at any point, there is one of these cones sitting there. Now, what does that cone tell you? It tells you what light does. So you imagine there's a flash of light at that point, and as time progresses, it spreads up. This is the spatial picture. Now I can get all the dimensions in, if you like. Here I have to imagine the cone. It's got another dimension, but think of it as a surface. But these sections through the cone represent the history of a flash of light in the middle, expanding out. So we have the red one and then the blue one, and the red one represents this section for the cone, the blue one that section. And here we can have all 2 dimensions of the surface, so that's it 3-dimensional altogether, and here we have only 1. So that's a good picture of what a light cone is doing. So a flash of light there would spread out, and you'd have imagining in spatial terms that thing spreading out as a light flash would do. What about the pass cone? Well, that you imagine a flash of light coming in and converging on that point. It's a very useful concept to have in space-time because it tells you causality. You see, things which can affect other things are always within or on the cone, and outside you can't influence that. So this is special relativity, where these cones are all uniformly arranged. This is general relativity, where they can wobble around in various ways. And the picture of this is a sort of illustration of what can happen in general relativity. The cones are not uniformly there, but you can see that information from inside can't escape because it would have to cross across the cone, and remaining within the cone it can't do because the cone's pointing in. So that's why light and any kind of matter is trapped inside this horizon. So these things you can understand nicely by looking at that picture and thinking a lot about it. And here's the material before it collapses, and then things can get out there, but the horizon is where the cones are tipped in, and even going at the speed of light, you can't escape from within it. Okay, so that's this general picture. Now, what's that? Well, you see, this is the sort of causal structure, or the light cone structure, or what can influence what structure of space-time. But there's one more to it. I should say there's a thing called the metric in general relativity, which it's described by 10 numbers. And those 10 numbers, 9 of them, roughly speaking, tell you where these cones are. And the 10th one is telling you what these surfaces in here. Let me explain what they are. They are what clocks do. You see, here I have a couple of clocks zipping along, and they're clocks, according to relativity, they don't keep a sort of universal time. That's one of the difficult things to understand. But different clocks moving in different ways have their own time. And you can imagine these are identical clocks, and this surface describes the first tick of the clock, the second tick, and then the third tick, and so on. So when you have these little bowl-shaped surfaces arranged inside the cone, that gives you the passage of time for regard to clocks. And that gives you the 10th component. So really it's the 9 of the ratios of the 10, but don't worry about that. So I should say the cones give you most of the information. The rest of the information you need are these surfaces. Now, key thing about this is that things which travel with the speed of light don't even notice those surfaces. So light itself travels along here. It doesn't care about those surfaces. The key thing is mass, you see. There are the two most important formulae, or famous formulae of 20th century physics were Einstein's E equals mc squared. That tells you energy and mass are equivalent. Max Planck, even before Einstein, had E equals h nu. H is a constant, and E and nu is a frequency. This tells you energy and frequency equivalent. Put the two together, that tells you mass and frequency are equivalent. So if you have a particle of a certain mass, it has a frequency. It has a normal particle would be very, very high frequency. But it's one of the reasons we have very, very precise clocks in nature, ultimately because of this. But it depends on mass. That's the point I want to say. If you have mass, you have clocks. If you don't have mass, you don't have clocks. And the equations of Maxwell, which tell you how electromagnetism works, they're completely invariant under squashing and stretching. So the angels and devils, they wouldn't know how big they were if they just had electromagnetism to control how they work. So things with mass are needed to give you the scale. So this is the crucial point of this description. The idea here is that you don't really have mass here or here. Why don't you have mass here? Well, you see, what's the most dominant? Well, we've got a lot of mass around here, but with black holes around, they swallow most of it up. And if you have huge black holes in galactic clusters, they swallow each other up, and eventually they start swallowing the cluster up. And they probably swallow most of it up. Most of the stuff running around will be photons. They don't have any mass. So that's the argument for here. If it's just photons running around, then this you don't care about, and you can squash things down, like in the Escher picture. So that's a key point. I mean, maybe you've got some rogue electrons running around, but then I have an argument why the mass should fade out there. But let's not go into that. That's a bit too technical. But going back in the other way, surely you've got lots of mass. Well, you see, particles, you've got massive particles, yes. But when they get hotter and hotter and hotter, they move faster and faster and faster, and that means almost the entire mass is in their energy, Einstein's E equals mc squared, so that the mass becomes completely irrelevant. And the closer you get to that point, again, mass becomes irrelevant. So this is the key part of the argument. Mass becomes irrelevant or isn't there, both here and here. And so the squashing and stretching is physically sensible. Now that takes a bit of swallowing, and many of my colleagues in cosmology, I may say, have a lot of trouble swallowing it. And I'm hoping, since you're not, most of you cosmologists, you probably have an easier time to swallow it than they do. But let me go on. This is the conformal structure where you don't have mass. That's fine. That's all non-mass things need to know. This is when you do have mass. Okay. Now, this was what I was just saying about the clocks. Now, what about the black holes? Well, first of all, there they are. I've put the black holes in the picture. These are represented by these red lines. Sometimes they swallow each other, and so on. And they're the red lines on the picture. But according to Stephen Hawking, and yes, I agree with him, I mean, I didn't know it before he said it, but you have black holes radiate. So they're not completely black, he says. They're a little bit cold. I mean, they're extremely cold, I should say, but not zero temperature. They have a ridiculously small temperature, certainly for the black holes we know are out there, ridiculously small. But in general, okay, when the universe expands and expands and expands, the black holes become the hottest things around. When they radiate away energy and radiate away energy and radiate away until they finally disappear with what I'm calling a pop. Pretty small compared with the energy in the whole thing. ridiculously small. How long does that take? Well, for the biggest ones, even this may be an understatement, for the biggest ones you would have to wait something like a googol years. Now what's a googol? 1, 0, 0, 0, 0, 100 zeros, years. That's the sort of length of time you have to wait. In fact, that's what started me off with this whole argument. I thought, how boring this universe is going to be. And when there's nothing but black holes, that's pretty boring. But to wait for this blasted thing to go off for googol years, even that's not the boring thing. It's when they're gone. That's boring. This incredible eternity of nothing. Okay, that's an emotional argument, I agree. But nevertheless, it was sort of driving force. And then I thought, well, who's going to be bored by this? Not us. How about photons? They're mainly photons. And it's pretty hard to bore a photon. Because, not just because they probably don't have experiences, okay, I'll give you that, but because, according to relativity, they don't have the passage of time. From creation to the infinity is nothing. They get right out to infinity, and there they are. So that was the sort of reason I was introducing these ideas. Okay, the black holes go away like this. They're there. They're going to pop. This is not... Everything I've said in these pictures up to this point is pretty well to scale. This is not to scale. This is way up there somewhere where they go off pop. Not even up there, right up the edge of the universe. Even that isn't good enough. So it's a long way off. Okay, so they disappear, pop. Now, I'm going to tell you, see, I thought when I'd had these various ideas, I could go on lecturing about this forever because nobody will ever know whether it's right or not. And so I thought, but then I had a rather uncomfortable thought. Well, you see, I mentioned these black holes. We have a, as I think I didn't say yet, but I'll say it, in our center of our galaxy, a black hole which has a mass of about 4 million times the mass of the Sun. Pretty big. We are on a collision course with the Andromeda Galaxy. Now, the Andromeda Galaxy has a black hole in it, which is about 40 times, I think, the size of ours, pretty much bigger than ours. In about a few thousand million years, we're going to collide. We're on a collision course, as I said. And in I don't know how many years later, the black holes will feel each other out, spiral each other out, and kaboom, they will run into each other. Kaboom isn't a good description because it's not a sound, it's gravitational waves, and you can't hear gravitational waves. Nevertheless, those signals will go out and reach the infinity. This is what I call the crossover surface between one eon and the next. It should be really three-dimensional, but I've drawn it two-dimensional. I hope that's all right. Now, this is meant to be us up here. There's us. And we're looking back. That's our past light cone. And this is the Big Bang, or the crossover from the previous eon to us. Now, here we have a couple of collisions in a cluster. Bang and another bang. And they create a ring here. And according to the equations, what you find is that these signals should influence the dark matter in the next eon, and you should be able to see signals. And so the claim is that you would, and they would be rather faint. There would be faint signals, either slightly warmer than average or slightly cooler. It's a bit of a nuisance because of alternatives, but they're slightly more uniform around the ring than normal. And I have a colleague, an Armenian colleague, Vahe Gurzadyan, who started to look for these things. And the key thing is that if this happens several times, as they will in a cluster of galaxies, you will have several of these bangs, and they will be centered at the same point. So this is a key thing. So I asked him, can you see rings like this which are centered at the same point? He came up with pictures like this. This is the picture of the whole sky. And what we're looking at is the microwave background. So this is this radiation coming from all directions. It's very slight variations in temperature. There's a one of the variations in temperature is due to the Earth's motion, because we're moving through this radiation, and you have to correct for that first. When you correct for that, you find a very uniform distribution of the sky, uniform to about 1 part in 100,000. So 1 part in 100,000, this temperature is the same, but little variations in this is what we're looking at. And what Vahe was looking for are these concentric rings of temperature which is more uniform over the ring than average. And he comes up with pictures like this. And I thought, I was expecting to see a pretty uniform distribution over the sky, if you see anything at all. And that's what he saw. And this was the WMAP satellite, which is a satellite which went around, I don't know how many years ago, and pretty good. And it showed what these temperature variations of the sky. More recently, another satellite, the Planck satellite, and he did it again for this. And again, you see these crowding of these. Well, let me go to the. You see, there's a picture of the centers, and I thought that doesn't look random to me. The claim is we're looking through into the eon prior to ours, and we're looking at clusters of galaxies. So each point here would represent a cluster of galaxies in that previous eon. Clustered, the clusters are clustered in the previous eon, so they should be clustered in our eon. So one of the claims here is that there's a lot more clustering, well, at least in the eon prior to ours, than people seem to think, which that may be the case. What are the colors? Well, that's another independent thing. The colored ones, the red ones, are the nearer ones. The blue ones are the more distant ones. So again, that's clustering, because the red ones are all together, and the blue ones are together, and the greenish ones are sort of in between. Pretty good evidence there's something there. And I claim this is, and some Polish colleagues of mine had a look, and using completely different methods, they also find a significant signal that these rings are there. I'm now not thinking about colliding black holes, I'm thinking about the black holes themselves. And this is their Hawking evaporation. So this is the black hole, and it evaporates away right up here. You see, Google years is way up, tucked up here. This is the Big Bang. This is what's called the last scattering surface. That's what you actually see, and the signal spreads out like this. The claim, that's the claim. Do you see these? This would be a slight raising of temperature. From here to here would be about 8 times the moon's diameter. So what would be a spot here goes up to 8 times the diameter of the moon. Do you see things like that in the sky? Well, Christoph Meissner and my other colleagues, I should say this is just what's called the power spectrum. You've got to put this in order to see something as significant. This is what you see. Now you see, what you do is you take this. If you think of the universe as like a balloon and you think it vibrating in all sorts of ways, well, the sort of noise, the frequency it vibrates is, if you like, the power here. Don't worry about what that picture is. If you're a cosmologist, you say worry about that a lot more. But the point is that you have to put this in, and with what you see, the observed power spectrum, you're then allowed to vary the different ways in which that balloon can oscillate, vibrate, and things like that. So that's what they do. And you make maybe 1,000 fake skies, which have the same picture as this, but in detail they can vary as much as you like. So that's the idea. And our colleague Daniel An, who's a Korean who works in New York, and he did this. He looked at 1,000 simulations. What we're looking at is little rings like this, and these are different sizes for the inner ring and the outer ring. And what they look is the temperature change from here to here. So if you're looking back at something where the temperature goes up in the middle, then this would be warmer than that, is the idea. And how much warmer is that than that? Well, is it anomalous? Is it average? Is it what you'd expect? You look at the power spectrum, look at all these random fake skies, and for 1,000 fake skies, he finds 0. That is to say, all these other numbers are the sorts of things you find for rings which are all the wrong shape and size for that signal. When you hit it dead on, you see none of the fake skies show this phenomenon. That means it's really significant. This is even quite significant because the number is quite small here, only 3. Well, it's here is about 6, isn't it? Okay, so people complain, oh, there's what you call a look elsewhere effect. Let me go into that. You were looking only after you saw the evidence, and so the probabilities are blah, blah, blah. So Daniel did it again, 9,000 more simulations. What happened to these zeros? Well, this one becomes 2, this one becomes 1. Ridiculously smaller than anything else. It's a real thing. In terms of probabilities, what does it mean? It means that the chance of this being a random effect is, well, the chance of it being real as opposed to random is 99.98% confidence. That's what you get from these figures. So it's really there. And it seems to be there. And what else can you explain? Well, I think that's the end of my... Yeah, let's not go into that. I don't have time to go into that, but if people want to ask me, that's fine. Thank you very much.